So we have here an absolute value inequality. So both together, both the inequality and the absolute value. And as we're looking at this, there's some gimmicky ways that I always talk about in class about how to remember how to set this up. For example, this is an absolute value is less than something, so less than and I don't know. Anyways, you've got an absolute value on the left-hand side and it's less than a positive value, it would have to be a positive value. But if it's less than a positive number, then you know that you're going to break it apart into two inequalities that involve the word and. And on one of them, you keep everything exactly as it is. So we have got the 7x and the plus 2, and we've got the less than and the 51. Now, on the other side, we know that there's this thing when we pull these absolute values apart, there's the possibility that the inside was positive and the inside was negative. Well, if the inside of the x plus 2 was a negative value, what that would mean is that I would have to flip the direction of the inequality and switch that 51 to a negative 51. And that's pretty much what I do, right? I write this exactly as it was. I keep this, I flip the direction, and then I get the opposite of the 51. So the motivation, the reason why I'm flipping the direction here is because this 51 is a negative that was pulled out from the absolute value. Either the absolute value was positive or the thing inside of the absolute value was negative. If it was negative, the direction of that inequality has to flip. Anyways, basically, I pretty much do this every time. If it's less than, I've got an and. If it's greater, I've got an or. And if it's and in both cases, I keep this is the same, the same, the same, and then I keep this, I flip the direction, and then I take the opposite. So that's kind of just raw memory tricks, but it's at least a start. Anyways, both of these inequalities, I'm going to do the same two steps to figure out what specifically the boundaries of x are. So I'm going to take away an additional 2. So I've got 7x is greater than negative 53. And then over here I've got that 7x is less than, and I'm taking away a 2 there, so that would be a 48. I'm sorry, a 49. 51 minus 2 is 49. And that's pretty simple, right? X has to be less than the number 7. On the other side, if I take the negative 53 and divide by 7, I don't think I get a nice number. I just think I'm getting that X is greater than negative 53 sevenths. Now I should be able to plot this on a number line and kind of see where the things are at. Remember, these are joined with the word and, so both conditions must be true in order to have solutions to the absolute value inequality here. So if I'm looking at this way over here, I could say this is the number positive 7, and my values are strictly less than that. And if I move way over here, 53 thirds, that's like negative 7 and I think 3 sevenths, so close to negative 7.5. So here's negative 7, here's negative 8. So somewhere in here is that boundary. And again, because it's less than the upper bound and greater than the lower bound there, it's all of these values in between. So any value of x that I pick that's in that range should work. And in fact, just to demonstrate, right, if I put the number 0 in, because it's clearly in that range, I get that 2 is less than 51, and sure enough, that's the case. So there's one more problem here right below. Let's take a quick look at that. So one thing to be cautious about is I am always talking about the absolute value being on the left-hand side. And so if you have to rewrite it, make sure you drag the whole thing around and take care of the direction of the inequality, make sure it matches the original problem. The other thing that's possible is that in this case, we've got the absolute value of 2x minus 6 minus 3 is greater than 9. Well, before I break this up, I need to make sure the absolute value is isolated, just like I would if it was an absolute value equation. So I'm going to go ahead and add 3 to both sides. That gives me the absolute value of 2x minus 6 is greater than 9, 10, 11, 12. And I did exaggerate the or in greater. I know it's greater, but I've got or because I'm going to create a compound inequality here that is joined with the or, meaning one or the other properties has to be true. And again, I'm going to keep this the same. This is a 2x, this is a minus 6, it's greater than, and then it's a 12. On the other side, I've got the 2x, the minus 6. I flip the direction of my inequality, and then I've got the negative 12. I need to take the opposite of that, so it's a negative 12. So in both cases, I'm going to add 6 to it, so I've got 2x is greater than 18, therefore x is greater than the number 9. And over here, I've got, if I add 6 to it, I've got that 2x is less than, I'm adding a 6, so less than negative 6, and divide by 2, that would give me that x is less than the number negative 3. And again, that's joined by or. So those are the bounds, and I'll just sketch the solution here, right? Here's the number 0, and then I've got 1, 2, and a negative 3. Again, this one has an open boundary, and x's are those things that are less than the negative 3. Probably be smart for me to write negative 3 right there. And then I got 1, 2, 3, 4, 5, 6, 7, 8, and 9. So here's an open boundary at 9. And x's are those things that are greater than 9. So anytime I pick a value in that range, it should be good. By the way, 0 would not work here. If I put a 0 in that, it would give me 2 times 0 is 0, so I get the absolute value of negative 6, which would be a positive 6, and then 6 minus 3 is 3, and then it would say 3 is greater than 9, which is clearly false. So it's just kind of nice to see that, yeah, this point right here will not work because it's not meeting either one of the criteria. It is not greater than 9, and 0 is not less than negative 3. But any point that lives in the yellow highlighted regions would be a solution.